In this project, you're going to be designing a hand-launched glider, balsa glider. You see an example right here. You're going to be evaluating that glider in a simulator. The details of the requirements and the constraints and what you have to turn in and so forth for the project are going to be in a separate handout. What this video is going to be focused on are the tools that we're going to provide you to be able to do this design and to be able to run the simulator. These are the different files we're going to provide you for this project. The first one here is the SolidWorks CAD. It's a modified version of an existing balsa wood glider called a Jetfire. But design's been modified a little bit, and then also the payload that's required to be carried is modified to be consistent with what's required for your specific project. The next folder here is the simulator. It's a modified version of my RBS Aero simulator, but it's been modified to focus just on this project. Some of the features have been reduced so that you don't have to worry about as many input files and different things. There are 3 different MathCAD Prime documents. Incidentally, these are all MathCAD Prime 11, and if you're unable to download Prime 11 from the University Software Distribution Center, I'll be providing the link for you in Teams. And then this file here is the actual project requirements file. Let's talk about the files that come with the simulator first. We're in the RBS Aero folder here. This first folder called Additional Support Documents, there's really nothing in there that you'll need. It has release notes and a coordinate system map. You may need to get into the interface folder. The primary thing you would get into here in the interface parameter. You can change screen resolution, display precision. Those are probably the only things you'll need to modify. Some of these other things are from different views. If you want to start with different views, a wider view, or put your pilot in a different location when you're running the sim, you can do that. But it'll probably be good enough for you to just use the default settings that I already have for you. In fact, for all of these things, you probably won't even need to get in here at all. There's some other files in here. For example, if you want to plot your output. Let's say you launch your airplane and you want to make plots of the airplane's flight trajectory. You can get in here the output variable map, and any file, or I'm sorry, any variable here that's not commented out with double lines. This is the comment that's used in this particular program. If something has a double slash in front of it, that's mean it's commented out, so that variable is not output. All of these variables are output by default, but you can comment those out. And for example, let's say you wanted to plot the U velocity, V velocity, W velocity. Well, you would just get rid of the comment, and now that variable will be plotted. So that might be nice for your report, so keep that in mind. This is the only file you will need, output variable map 0. You won't need 1 or 2. The other thing you might want to change, the variable display map. These are the variables that will be displayed on the screen while you're flying. Okay, I think I have the ones that are most important for you here, but you could change those as well. But those are the only things you would need to modify in this folder. Log files folder you won't need, models you won't need. The output data this is where your data is going to be. If you want to, for example, when you talked about outputting the variable map here, where that data will show up when you escape out of the window. So you're running the sim. Once you escaped out of the window, all of the data is dumped into this folder, into flight data body 0, comma delimited file. You can see an old one here, and this is what it looks like. You won't need the shaders file to get in there, or the textures file. You will need to get into the vehicles file. I'll show you that in a minute. Here, this file will be useful to you. This is the reduced instruction set, and then this is the executable. Just double click on that and the sim runs. Let me get into the vehicles folder here. Here's the baseline Jetfire for you. And there are different attribute files that you put in to run the airplane in the sim. The key difference between this sim and any other sim you'd find out there, the key objective in the design of this sim was the dynamics accuracy. Unlike all the other sims out there, you typically put in an airplane geometry. And then, you put in the wings and the tail and the fuselage and so forth. And then in the background, a simplified aero model is run, one that can run very fast. And you get your motion. Now, most simulators that are commercially available out there, their focus is more on graphics. This one is really focused on dynamics. So in this case, in this sim, all of the aero, Stabcon, propulsion, everything can be analyzed offline, even using CFD or whatever type of tools you might like to use. You're going to use their MathCAD documents. And then you put those aerodynamic and stability parameters into these attribute files. The only ones that you'll be needing to mess around with are the airplane aero attribute file. We'll be coming back to this one in a minute. And the vehicle attribute files. So once again, we'll come back to this one as well when we start using the sim. Okay, so once you do the analysis, you'll be able to modify those files. Now the instruction manual here, I think you'll find useful. The instruction manual shows you how to, if you want to change the user interface, some of the key commands that allow you to change your view, slew the camera, and so forth, and some other information. A little bit of troubleshooting. By the way, most of the types of problems people will have with this are settings on the graphics card, which are addressed here. And then another thing is, if you modify those attribute files, the input files, and you leave any blank lines in there, it'll cause problems with the read. So you don't want to have any blank lines. One more thing about these simulator files, you'll notice one file here called jetfire.obj. This is the graphics file. This is the graphics file that actually shows you this glider. Okay, changing that file doesn't change the aerodynamics at all. It's just for the graphics. Your aerodynamic, stability, and control and everything else are in those attribute files. I mean, you could basically put in anything that you want for that graphics image. So, for example, if you're doing this project and you change the design of the Jetfire, which I encourage you to do, you can still actually run the sim with this OBJ file for your graphics. But if you have the time and you want me to show you, I'll actually show you how to take your CAD file and modify it so that you can actually see your airplane flying in the sim instead of this Jetfire one that I provided. Okay, let's look at the CAD file. I'm providing you with this modified Jetfire that I told you about, basically a balsa glider, and you can change the fuselage on it, the vertical tail, the horizontal tail, the wing. You notice the wing that I've got drawn on here is just a rectangular wing. It's got just a couple of degrees of dihedral on it. I've got it set up to automatically calculate the CG and place a coordinate system there for you. So it just makes things so much simpler and faster for your calculations. All of the parts are balsa wood, and the details of what you're allowed to do in terms of the design are in the file I told you about. I won't get into that now. I'll just show you how to use this. But this little metal clip here, it's 4 grams in weight in this particular case, and it's made out of steel, and you'll notice here. Actually, let me get kind of a side view. If I move it around, and then if I hit the rebuild, it'll actually recalculate where the CG is going to be. And so no matter what you do, if you change the wing or the fuselage or the tails and hit rebuild, it'll automatically calculate this CG, and you'll notice it's going to make things so much faster for your analysis. So what you might want to do instead of creating your own document is that you make a copy of this SolidWorks document that I give you, and then you just modify this. So you modify the wing. You can move the wing anywhere you want. You can change the fuselage. You can change everything. You can carry the payload at a different location, and then all of the automatic features will continue to work, and it'll save you some time so that you can really focus on the design and the Stabcon part of the project. Another really nice feature of SolidWorks is that you can calculate all the mass properties of something. So I've got it already set up to do that for you. So, for example, you can come in here and you go to Evaluate, and then you click on Mass Properties, and you'll see this window pop up, this Mass Properties windows. And you can change the values. You can change the output, what this is going to be in. Unfortunately, it doesn't have slugs, so you'll have to divide by 32.2. I've got that already set up for you. But right now, for example, this is in mass. You know, this entire glider with the payload and everything is about 10 grams. But what's really slick about this is that you notice here it'll also calculate your inertias. Now be careful of which one of these to use. You want to click on this window and select CG so that it's going to report coordinates relative to the CG. And then you can come in here, you can actually see the little kind of this pink coordinate system actually shows you where it thinks the CG is. So you see it actually matches my calculation of the CG. So that's good. And then you see here, you're going to look at the last one of these, moments of inertia, in this case grams times square feet, but you want to modify this. You'll see in the MathCAD program later to match what you're doing, the units you're going to use. But taken at the output coordinate system, which is the CG, Here's IXX, IYY, and IZZ, and then IXZ. Those are the only 4 that you're going to need. So you see that'll save you a lot of time than trying to calculate those by hand or estimate those by hand, or Excel or writing your own MathCAD program that'll do that with the parallel axis theorem. You can just get it immediately right from SolidWorks. Let's go through the recipe that's going to be required to do the design in this particular project. The first thing you need to do is figure out what design variables affect your primary design goal. So for example, it might be endurance. And so what is it about this airplane? You know, its wing area, its operating point, its lift coefficient, drag coefficient, so forth. What is it about the design that optimizes endurance? Okay, once you understand that, and I give you some hints and some recommendations in the project handout to help you go through that. Once you have that information, then you're ready to start with the basic aerodynamics. You need a drag polar for this airplane. All these different aspects of your airplane design, for example, your wing size, your wing geometry, your fuselage size, your tail geometry, all of those things, anything you change affects the lift and the drag. So we have to be able to analyze that first. So I give you a code here called APG, Aircraft Polar Generator. And I've got it set up for the Jetfire example. And I provide you with the airfoil data, and so we'll just assume that this doesn't change. So this is the airfoil data that you're going to be using on your glider. Incidentally, whenever you see anything in yellow, what that means to me is that's an input, and wherever you see anything in green, that's an emphasized output. Okay. Well, this is actually something you don't need to change anymore. I've got that input already done for you. Okay, so you can come down here and you can see all the different things that you can input. Your wing area, your wing span. The solve mode, you just leave this one. Sweep angle, taper ratio, poly taper start location. So in other words, if you want the wing, let's say that you want the wing to be rectangular out to 0.5 of the span and then taper down from there, you can change this. Wing twist, you probably won't want to change that. This is this velocity is, you put in an approximate velocity for your cruise, and it allows you to calculate the Reynolds number for skin friction drag. The fuselage information is in here too, so you put in the fuselage length, the max fuselage width or height, and the fuselage wetted area. Incidentally, all of these things, everything here you can get right off the right off the CAD. Right? So for example, if you want the fuselage length, I just come in here and I can click on the measure tool, and I can measure from that point to that point pretty easy. In this case it would be dx. If you want to know the wetted area, if you just click on an area, it'll actually tell you what the area is. Now, in this particular case, that's just the side area that I've clicked on. So if you want the total wetted area of the fuselage, for example, there are two sides, so you'd have to add up all that area, and then you need to also add up the areas all the area of the entire fuselage. But once again, by having this nice SolidWorks tool already set up for you to do that, it's really quick, so you're not spending your time making measurements and entering things in Excel and a calculator. You can focus on the design and optimization. Okay, you come in here. This airplane has a horizontal tail and a vertical tail, so those are both ones for yes. This is the horizontal tail area, projected area, right? Planform area. So once again, that could just be obtained by just doing that. Same kind of thing you can do for the vertical area. And then that's it. That's everything that's needed for your drag polar. And then the code does the calculations, and it gives you a drag polar, CD versus alpha, CL versus alpha, and all this information. The most important information is going to come out in this output file called polardata.txt. Okay, so what I'll need to do is if I calculate the worksheet, you see, okay, once it turns green, you notice a new txt file in your folder. If I double click on that, you notice what I get is 3 columns. This first column is alpha, the second column is CL, the third column is CD. Okay, so that's going to be important information for us to put in the sim later. Once you've done the aero, you need to calculate the static stability of the airplane. So that's what the Stabcon S, the reduce file here for the Jetfire will do for you. If you scroll through this, you can see basically what it does is use the complete buildup method that you've been taught, but it has all the equations in it and more that you've been taught. And so it'll actually use the airfoil data. It builds up the contribution from the wing, the horizontal tail, the fuselage, or I'm sorry, the vertical tail, the fuselage, basically everything. And it calculates the complete stability and control. You can look in the individual areas if you want to see what the equations are, but you'll be familiar with them since you've done them. But here are the airplane geometry inputs that you'll need. I've got it broken down by the different airplane parts. So here's for the wing, the horizontal tail, the fuselage, the vertical tail, and then the fuselage again for the, yaw. And then there's additional inputs, taper ratio, wing dihedral, and so forth. We'll get to those in a minute. Some of these inputs you've already done, you're already familiar with because you did them in the drag polar. You'll need to calculate the mean wing arrow chord here to put in. And so once you've done that, you put that information in, and then here you start putting in the information for the tail. Let's do one of these. Let's look at this specifically because this is a little trickier. Okay, first question you're asked here is, does it have a tail? Yeah, it's a conventional tail, so that flag is a 1. And then you have things like your tail area, your tail span, your tail sweep. And then the other thing it needs is the distance from the wing mean aerodynamic chord leading edge to the tail mean aerodynamic chord leading edge. Okay, well, That's really easy to do in the SolidWorks. You'll notice here, that's what all these lines are. All of these lines that I have showing, these are all the sketch lines for the horizontal tail and the vertical tail. And you can see here, I've got the leading edge, trailing edge drawn. You see there's the quarter chord, so you can calculate this angle right here. You can calculate the sweep angle just by, for example, we could do it this way. If we, let's see, turn off the evaluation, and we open up the horizontal tail for analysis. And if I look at sketch 3, I can see all the information here. So there's the horizontal tail span, which, was required. The tail sweep, 14.8, so on. So all that information's put in there. What's also calculated in this case, for this tail, now your tail may be different, but for this tail, I calculated the mean aerodynamic chord for this straight tapered wing here, and it happens to be 0.98. And so 0.98 is this line right here, this distance right here. There's the leading edge. There is the leading edge of the mean aerodynamic chord of the horizontal tail. So what this was asking for, this 0.395 feet, was the distance between the wing mean aerodynamic chord leading edge to the tail. Okay, let's go back and do that. Now this wing is rectangular, so it's really easy. It's the leading edge anywhere. So I can click on that leading edge, and then you see on the sketch right here, this little point right here is going to be the leading edge of the mean aerodynamic chord of the tail. And boom, there, that dx there, 4.741 inches. I could write that in feet because you can have this output in feet. But that's what's asked for here. This is in feet. Everything here is in feet, but that's where the 0.395 comes from. Okay, so by having these things pre-drawn for yourself already on your tail, on your geometry, you can do this input very quickly. Okay, same kind of thing. You come in here in fuselage. This is easy. Fuselage, that's the full length. This is the maximum fuselage width. This is the distance from the fuselage front to the max fuselage width. Well, it's 0 in this case because you see this airplane, its maximum width is this. I think that's 1 inch. Well, it happens at the origin all the way up here, so it's 1. Or I'm sorry, it's 0. And then here, fuselage front to wing mean aerodynamic chord leading edge. Now, if you have a tapered wing, you're going to need to calculate the mean aerodynamic chord, and then you just you just draw that on here on the wing, just like I did it on the tail, and then you can just calculate. Just click. It's not clicking for me. There's the leading edge, and there's the leading edge there, and then that's basically 2.8 inches back. In my case, for this rectangular wing. Your wing may be different if you put a taper in it. Okay, so we can do the same kind of thing for the yaw calculation. The wing MAC leading edge to tail MAC leading edge. Same kind of thing, but this time, here's the vertical tail. Here's the MAC of the vertical tail. So I can just calculate. Let me click out there. I can calculate the distance from there to there. Boom, and it gives me that number very quickly. So there's the tail area of the vertical tail, the tail span, number of verticals, and then I do the same kind of thing for the fuselage again. Inputs I need for roll stability. Taper ratio is 1. Wing dihedral, you can measure it, but the dihedral angle of the main wing is actually 2 degrees. ZT is the height of the tail, the horizontal tail, above the CG. That's the distance of this tail above the CG. The vertical tail, this is the height of the vertical tail MAC above the CG. So that distance is the distance from this CG to, oops, it's not working for me. Sometimes it's hard to be able to click on that point. Just click on the point there, up to this point. Having trouble. I may need to restart SolidWorks, but basically the distance, what I'm trying to click on is the distance from here to here. Okay? That is the vertical tail MAC. Okay? And then this last one here is the wing mount location above the CG. And that is the wing. How high is the wing mounted above the CG? Okay, this location relative to here. It's essentially 0. I think I had it minus 0.01. Okay, so that all that information is very important in there for roll stability. Then the last couple of things you need, here's the wing incidence. In this case, I've got a wing incidence of 0. The tail is mounted on here at minus 3.6 degrees. This angle, you can see I've got it set up to do the calculation. That's set up for minus 3.6 degrees. And then your CG. Here's your CG location. I've got this set up. This is for the 4-gram payload in the nose. That's the default. Okay? So one of the things you're going to need to decide when you're ready to do your project is where should the CG be? Now I just, for this starting location, I've got this thing set up so that the the payload is out here on the nose and the CG comes out to here. But what you probably want to do is actually make your CG change and start at a more reasonable position, something that's more traditional. Let's say, oftentimes we use the quarter chord of the main wing. So let's say you wanted your CG to be around the quarter chord to start with. What you need to do is figure out, okay, what do I need to do in terms of, I could move the wing too. I can actually, move the wing forward. I can change things around. And okay, so you can figure out here, okay, if I wanted to end up with a starting point like this, I'd need to actually maybe move the wing or the payload and modify the nose, or both. Okay, but I'm going to leave it where I had this originally, because I'm just going to show you how to analyze it based on the location I had in this particular case when I started. So the CG that I've chosen is going to be this location here. And so that's minus 0.01. Okay? Then the other thing you're going to need is to figure out, where do you want to trim? I'm going to say 3 degrees. Okay, and I'll show you that in a minute. And for 3 degrees, I'm going to end up with, that'll give me a lift coefficient of about 0.207. Okay, so how do you choose? You might ask me, how do you choose what trim angle of attack you want? That's where what I said in the beginning comes in very handy. If you know what it is you're trying to optimize, for example, if you're doing a project where you're maximizing range, that optimizes at a different angle of attack than endurance. Once you know approximately what you want to do in terms of your optimization, you can know what your optimum angle of attack is going to be. Now the angle of attack is going to give you the best performance. That's where you're going to learn here that your stability and control can actually benefit your aerodynamics. The pilot's not having to maintain this. You're designing this airplane on its own to fly at whatever angle of attack is best for your particular mission. So I'm just going to keep it 3 in this case. Okay, if I scroll down now, you see all the green. These are my outputs. By the way, over here on the right, you can see, this is actually where the CG is. The red is where the neutral point is, and you can see some of the outputs. This is the neutral point location in percent chord and in distance and so forth. Here's all the roll stability. Here's the dihedral effect. This is the static margin and pitch. As you can imagine, where I've got this CG, this thing has a huge static margin. It's almost 50%. Here's my CM versus alpha, this negative, so it's obviously stable. Here's my static stability in yaw. It's 0.065. This is the value that I've told you that in the NASA TN document, you'd like, bottom line, you basically would like this to be somewhere in the neighborhood of between 0.05 and 1. Okay, and then I've got a graph here. The black line is your CM versus alpha curve for the whole airplane. The green curve is the contribution from the tail. The blue curve is the contribution from the wing. The purple line is the fuselage. You can see the fuselage is doing nothing. But this airplane, where I've got the CG set up, this airplane, you can see here, it's going to trim at about 3 degrees. That's why I went back here and I set this 3 degrees, because that's where it's going to emphasize the analysis, right around 3 degrees there. Okay, you see that airplane is very stable. You also see in the yaw conformation here a positive slope, so it's stable in yaw. And then finally, what you get is an output here, the output file called data long and data lat, or Stabcon long and Stabcon lat. So if I come over here, and if I look at my output files, oops, I'm sorry, I need to hit calculate worksheet. And then once it calculates, okay, see Stabcon lat. And Stabcon long. Okay, Stabcon long here, this first column is alpha, and the second column is CM. Okay, so I've got my static stability for this particular configuration all done. Now what I need to do is input it into the sim. First thing you need to do is come over here and open up the airplane aero attribute file. Always make sure that anytime you change wing area, mean aerodynamic chord, or wingspan, you change those here. Okay, now what I've got is the longitudinal static stability part of this input file are these four parameters here. Okay, alpha, CL, CD, and CM. Remember, CL and CD came from the polar generator. CM came from the static stability analysis. Okay, so I'm going to delete this first. And now what you're going to do is open up your APG polar data, and you can copy this and you can put it into Excel. And then you come over to your Stabcon long data, open that up, go back to your Excel file, and you'll see this first column here, this was alpha, this was alpha. You'll see that it's already set up for you, it's already synchronized. So all you need to do is basically take the CM data, drag it over here, and then copy these first four columns. Copy that. We'll close out of this. And basically, we just need to put it into that first file. Actually, let's see, I believe I made a mistake here. I deleted one line too many. Okay, I'm sorry. Here we go. Delete those lines, and then I'll paste. There we go. I don't like how this data is shifted. Excel, if it's a 0, it actually gets rid of the trailing decimal. So I just like to put in some additional zeros here so that it all lines up. But there you go. Your longitudinal stability parameters are in the parameter file, alpha, CL, CD, CM. Okay, so we'll save that. Now scroll down. Here, alpha, CX beta, CY beta, CN beta, these are all the lateral stability parameters. We've got to change those out. So we'll delete those. Go back into your file, your Stabcon lat. Those are already done for you, so you just copy those. And you paste them back in. And there, you're all done. Okay, so there's your static longitudinal information, your static lateral information. Now make sure you don't do like a mistake like I did, is delete an important line here, like your header. Or this is another thing that people get in trouble. Like if you find that you have an extra line in here like this, it'll cause a problem with the read. So make sure you delete any extra lines. Okay, there's only one more input that we need for the aerodynamics attribute file, and that is the dynamic stability derivatives. These. So CZQ, CMQ, CYP, CNP, CLP, CYR, CNR, and CLR. Everything else here you won't need, but these you do need, and we get those from Stabcon D. the dynamic analysis of this airplane. You're going to notice that parts of the inputs of the dynamic analysis file are going to look similar to the static inputs. So all of the buildup is done for all of the different parts of the airplane, and all the stability derivatives are calculated for you automatically. So, like I said, a lot of these parameters, you will see they are common to what you already did for static. So you can just re-enter them or copy and paste. Don't try to copy and paste a bunch at one time. Do them one at a time, because they're not always in the same order. But there's the wing and the tail and the vertical tail and the fuselage. So I don't believe there's anything there that's significantly different that I need to show you. I've already shown you how to measure those. Here's some additional input. The CG, now that's the same. You put that in the same, make sure that's the same as what the static stability CG was. You put that in there. Here's the overall weight of the glider. That you get right out of SolidWorks. I showed you how to calculate the mass properties. This trim lift coefficient, whatever you ended up doing over here in your Stabcon S. So remember I told you you kind of want to design this around designing for trimming at a particular angle of attack. That's where it gave you your trim lift coefficient. So at 3 degrees angle of attack turned out to be about 0.207. So that's what I made my trim lift coefficient in the dynamic analysis, because one thing you may or may not have realized when you're doing all your stability parameters is that they're not necessarily constant with CL, with lift coefficient. In particular, some of the lateral ones, having to do with the hedral and roll stability and so forth, they actually depend on lift coefficient. So that's why you got to try to estimate that number and put it in. Okay, and then the last thing you need to do the dynamic analysis is the inertia input. Now this code will do it in two ways. It'll actually use this little model I've got over here. You know, this is the assumed geometry. And then depending on all of the inputs you put in, it'll estimate it for you. But you don't have to do that. You can use manual inertia input, because all you've got to do is go to SolidWorks. You come over here to SolidWorks. You do your mass properties. And in this case, you've got to go to options, and instead of feet, I've got to use pounds in this case. And so what it does is it calculates these inertia in, for example, pound feet squared. So it uses that evil unit, so-called unit, but what I've already got it set up in the MathCAD document over here. Here you basically just put in this number right here is the number you get out of SolidWorks, and then you divide by 32.2, and then the actual, you get the slug unit, which you need to actually do the inertia. So there's your inertia matrix. So now you've got everything you need. And it calculates for you your longitudinal modes. So they're your longitudinal routes and your lateral routes. So you see over here, you can see the phugoid routes, which are these two, low damping and low frequency. And there's short period routes, high frequency, high damping. Here are your lateral routes, your lateral modes. This one is your spiral mode, very close to the axis. So this thing is slightly unstable, but its time to double is going to be like many seconds. There's your Dutch roll, and then there's your roll route. Okay, so that you can take a quick look at your routes, and you can see if there are any problems there. And then the valuable input for the sim for you is this output file called ratederivatives.txt. You come back in here and, oh, I'm sorry, I forgot to hit the calculate worksheet. So we'll let it calculate. Once the circle turns green, there it is, the RBS rate derivatives. Open that up, select it, and I need to open back up the airplane arrow attribute file. And you see down here, delete that and then copy and paste. And then what it does sometimes, and this may or may not happen on your computer, times it bunches the numbers together. So you kind of, when MathCAD plots them out or prints them out, so you gotta make sure, okay, there's CMQ, this one's CYP, that one's CNP, I'm just hitting spaces, CLP, CYR. This, my whole sim is written in C++, so it just ignores the spaces. CNR and CLR. And that's it. Save. And the arrow attribute file is completely done. Before I can run the sim, I need to enter data into the vehicle rigid body file. Okay, most of this stuff I already have set up for you. You won't need to change it. This Jetfire OBJ, that's the graphics image file that'll be displayed when your airplane's flying. I mean, you could have a scan of your face and make it an OBJ file and have it flying around. It doesn't affect the aerodynamics at all. It's just for the graphics. This next input is your initial position. So this is going to be based on the rules of the project. This is your initial orientation. These are your initial launch velocities. That'll be based on the project as well. Really, bottom line, this is the initial angular rates. Those are all 0. Basically, the only thing you need to modify in this whole file is just the weight. So whenever you change your design or whatever and the airplane weight changes, you put a new weight in here. And then you need to put in the 4 values of the inertia matrix. You see these numbers? They may look familiar to you because those came from here. Okay? You just make sure that you put those in properly. You use the proper notation so that the C++ code can read it in properly, and that's it. So everything has been input, and this airplane is ready to fly. Okay, let's launch this airplane. Okay, when you double click on the executable, actually let me show you how to do that just in case. So you double click on the executable and you'll get this console window. Select a vehicle. Well, I've only got one airplane in this. So hit 0, hit enter, and then it reads in all of the information, does all the preliminary calculations it needs to do. And then what you get here is the graphics window. And so there's your glider, and it's at the our airfield, the UAFS airfield. There's the Ramada down there. You can use the WASD keys to move yourself around. This is like the fixed location. You know, you're kind of up in the air. You're in a hot air balloon or something, and you're going to launch this glider. There are 3 different toggles. If you toggle V for view, you can toggle yourself into, this is rear view. So you'll always be, it's sort of a pilot's view. You'll always be in this perspective relative to the airplane. And if you hit this view here, you're actually moving with the airplane. I'll show you that as we launch. Okay, so we're ready to launch. Now, in this particular case, we're at 120 feet high. The requirements for the contest are that you have to throw the airplane with 10 feet per second forward and 2 feet per second lateral. And so, in other words, just to show that it's not a perfect throw, so that it'll excite both the longitudinal and lateral modes. And so if I throw the airplane, there you can see its dynamics. It's using the phugoid mode. And you'll see the different parameters changing up here. You know, the roll angle, pitch angle, heading, angle of attack, airspeed, which is in knots, by the way, is VI. Look over here at this number, T. T is 15 seconds, so that's going to be your score. This airplane would get a score of 15. If I hit R, it'll restart everything. And I'll show you if I change my view. If I change into this view and then launch, you see now I'm riding with the airplane. You see the phugoid in the short period? And I can actually move my view around. That's just with the WASD keys. Okay, so I got the same score, as you would expect. I'll show you some other things here. If you launch, you see the lateral modes too. Kind of, you saw a Dutch roll there. If you hit the space bar, you can pause at any instant. Won't affect the dynamics. So we're descending at 13 knots. Trim speed is 13 knots. There's the altitude right now, 63 feet. Rated descent -7 feet per second. And you can see there's the alpha heading. Pitch angle is pretty severe because, this thing is really nose heavy, right? Where I put that CG, it's pretty far nose down. Okay, and that's how you use the sim in this project. And now you would go back and you kind of go back to the first step of your design again and say, okay, well, I've got this. Now let me try some other thing. Let me try to optimize this or that. Or, you can even, I'll show you, you can even use the dynamics of the airplane. You notice how this airplane, because its trim speed is so high, its design trim speed, because I made the design lift coefficient so slow, that throwing it at 10 feet a second is too slow. And so it dives. It requires the airplane to dive and use the phugoid to pick up speed. So it's wasting. You see, look how much altitude it wastes. Instead of using that altitude to glide. So if my goal was endurance or range, I could do much better than this. So you just go back and, you go back to the basic aerodynamics. Maybe there's a lot of different parameters you can change, right? Let's just go back, and if we look at the airplane again, just think of some of the key things you could change, even on this glider, without changing anything in terms of its overall design. Like, you could keep the wing the same, just moving the CG around would allow you to trim at a different airspeed, which may be more optimum for this airframe if you're trying to do endurance. You can move the wing. You can change the incidence of the tail, right? If you made this tail incidence even more negative, even at this forward CG, it would want to trim at a higher angle of attack. But then, of course, with the rules of your contest, every year it's a little bit different. But you can change things about the wing, the wingspan, the taper ratio, and then of course, you could always change the tails. It doesn't have to be this big. What you may find is that when you redesign your wing, maybe the tail is got too much size, and so you could improve its drag by making it smaller. Maybe you don't need as much stability as designed into this one. So there's a lot of things that you can change to really optimize the design. One last thing I'll show you is how you can plot your output data if you like. Go back to the sim, and we'll go ahead and launch this airplane again. And then after the airplane touches down and you're done, let's see, 14, 15 seconds. Okay, we're all done. Come up here and kill the window. Close the window. Then remember I told you about the output data. Now you have to kill the window for this to work because it stores the data until that kill window command is executed. Come in here and you look at this flight data. And remember, you were able to select all the different inputs that you wanted to plot. And so here they all are. So I could come in here and I could, let's just say I wanted to plot altitude versus time. And I could come in here and insert a chart. And there it is. And you see, remember there was that kind of dip. You see sort of that phugoid looking motion there. But you could plot any of the parameters you want. You could actually, might be interesting. You might say, hey, what did lift coefficient do during this flight? And so I could come in here and plot this. And it's kind of interesting, as you imagine when it first dives, lift coefficient dropping quickly, and then it recovers a little bit, and then settles around 0.2. But you could plot the trajectory, rate of climb. One more thing. Let's try. Let's see what happened to angle of attack. During that flight. Now this is in radians. Initially it's moving very, very slowly. So, the alpha was unrealistically high and then very quickly drops, and you see it achieved a steady state of 3. Well, that's interesting, isn't it? Because we predicted in the stability and control, when we did static stability, remember the CM versus alpha curve went right through 3, so that would be its trim angle of attack. Well, there's confirmation that, 3 is where the airplane's trim was. And the dynamic stability was how the airplane got to that equilibrium point, that trim point. So have fun with it, and I think you'll learn a lot.